So we will continue the treatment of Bose gas using the grand canonical perspective. We have seen that for each given state, so it's bosons and grand canonical ensemble. And we have seen that the probability, the average number of particles at given energetic level epsilon was 1 over e to the power beta epsilon minus mu minus 1. Right. And this minus 1, just this minus 1, this makes everything different from the fermions. Okay. That's the only difference mathematically as we see, and it makes a crucial difference. Now, we looked on the system of 3 energetic states, and now let's generalize it to a free boson gas. So free Bose gas. The extension is very similar to the way how we made the extension from 3 states for fermions, 3 energetic states for fermions, to a free Fermi gas. The same happens over here. Okay, we have energy, we have a box of volume V. The energy of all the bosons that sit inside are just the kinetic energy. Okay. Therefore, so epsilon equals to h bar divided by 2m k squared. H bar squared. And we have to start from energy 0. Kinetic energy cannot be lower than 0 in our case. It's not exactly 0, it's just a little bit above 0. Because if the electron or if the particle has a specific energy 0, well, it's not cooling and we know where exactly it has to be. So the lowest, the ground state is not 0, it's a little bit above it. Alright, so what we want to write is the total grand canonical potential. So, grand canonical potential, which is minus 1 over beta log of 0. The moment that we know that what is the grand canonical potential, we can obtain any other value by taking the appropriate derivative. Right. Okay, so Z is the multiplication over all the possible epsilons that we have in our system of Z epsilon to the power of G, where G, or G0, let's call it, G is, what is G? What is G?
Degeneracy?
Mm-hmm. Exactly. Degeneracy. Great. Now, what is Z epsilon? Z epsilon is, do you remember what Z epsilon is? We obtained it last. Is just 1 over
1 minus
1 minus e to the power minus beta epsilon minus mu. Okay. This is our Z epsilon for any given energetic level over here. G, well, it depends on the spins, the allowed spins for our bosons. So those are Z epsilon. So therefore, we can write down our ground canonical potential in the following form, which is minus 1 over beta log multiplication of all the possible epsilons we have inside of 1 over 1 minus e to the power minus beta epsilon minus mu. And that's it. Okay. Now the problem is to perform this multiplication. Of course, we don't need to perform the multiplication because of the log over here. Okay, we have and the factorization, so it's simply minus 1 over beta, a summation over all possible epsilons of log of 1 over 1 minus e to the power minus beta epsilon minus mu. Okay. And we can write it down more simply by saying it's 1 over beta, summation of epsilon, log of 1 minus e to the power minus beta, epsilon minus mu. Okay. Now, how we continue for the case of the fermions, instead of taking the summation, we somehow transform it into integration where we have d epsilon, which is the density, d epsilon. And whatever stands over here will stand over here. The bounds of the integral are epsilon starts from 0 and goes up to infinity. This is our kinetic energy, so 0 up to infinity. To remind you what is d epsilon, we obtained it for the fermions, and it's exactly the same for bosons. Those are the standing waves. We have particles that somehow survive inside the cyst, inside this box. You have to solve a Schrodinger equation. Schrodinger equation, as you all know, it's a wave equation. So eventually all the wave equation with boundary conditions that the probability density function or the wave function is 0 on the edges. Okay. Those reflecting boundary conditions. So the only solutions are waves or standing waves. Therefore, we have a discrete spectrum of the particles that can be inside the system. And this idea that we have been using since the model of Debye for writing down this density is exactly the same over here. So d epsilon is what? It is v divided by 2 pi squared k squared dk d epsilon. That's it. Now, what is dk d epsilon? So we can write down the connection between k and epsilon as k equals to 2m divided by, or 2m epsilon divided by h bar squared square root. Okay, so therefore dk to d epsilon equals to 2m h bar squared multiplied by 1/2 square root of epsilon. Okay. Now, and case, all right, so now we plug everything inside. We obtain that d epsilon equals to v divided by 2 pi squared. K squared is just this guy squared multiplied by this guy squared. Okay, so, and we have 1/2 from over here. So what do we have? We have 2m divided by h bar squared to the power of 3/2 multiplied by square root of epsilon, and this 1/2 is going to modify this 1/2 over here. So we can write down as 2 pi squared. A little bit of algebra, and we have our d epsilon. Okay. Now we can plug everything inside this integral and try to solve. Oh, so what I have forgotten something. Exactly. So there it was g0 over here. and the g0 goes to g0, or it's not g0, it's just g, here have g, and that's it. Yeah, so it's g divided by beta. Okay, so we have an integral expression for our grand canonical potential. And this expression goes as psi equals to g divided by beta, an integral from 0 to infinity. We have log of 1 minus e to the power minus beta epsilon minus mu multiplied by v divided by 2 pi squared 2m divided by h bar to the power of 3/2 squared over here, square root of epsilon d epsilon. Very nice integral. Okay, so the goal is to bring this integral into something more acceptable, okay, something more nice, and to work with this. The final idea is not just to obtain psi. The final idea is somehow to connect between the average number of particles, total number of particles inside the system, and mu. Remember where the interesting physics came from in the fermion case, right? So we calculated, we tried to calculate mu Fermi, and we discovered that since in our system the average number of particles is very, very, very large, all the particles in the energetic spectrum have to pile up on top of each other. This gave an enormous mu Fermi and an interesting physics, right? So the same idea we apply over here. We take this psi, we make out of this ugly expression something more comfortable, we compute the average number of particles, and then we try to observe an interesting effects coming from what happens to mu, what happens to all the system when n is large, right? Okay, so a lot of algebra is coming our way. Buckle up. All right, so what I want you to do, first of all, let's try and get everything out of the integral that's not related to epsilon, okay, which is mainly this ugly stuff over here. So we have g divided by beta multiplied by v divided by 2 pi squared 2m h bar squared to the power of 3/2, an integral from 0 to infinity log of 1 minus e to the power minus beta epsilon minus mu square root of epsilon d epsilon. Let's call all of this as a for simplicity. Okay, now I'm looking on this integral. I want to solve it, and I will try to solve it by using integration by parts, right? So what I have an integral from 0 to infinity of log of 1 minus e to the power minus beta epsilon minus mu multiplied by square root of epsilon d epsilon. Now I claim that I can integrate this part, and it's easy to take derivatives out of logarithms, right? So I will just say the following. It is epsilon to the power of 3/2 multiplied by 2/3 multiplied by log of 1 minus e to the power minus beta epsilon minus mu between the limits 0 and infinity, okay, minus an integration from 0 to infinity. And now I have to take 2/3 epsilon to the power of 3/2 and take a derivative of this guy. Okay. Now the derivative of a logarithm, it's always very easy. It's 1 divided by 1 minus e to the power minus beta epsilon minus mu. Okay. Now inner derivative is just minus 1. So we have minus 1 multiplied by e to the power minus beta epsilon minus mu. Now the derivative is with respect to what? Epsilon, okay? So we also have minus beta over here, d epsilon. Yeah. Right? Looks reasonable. Now, the first part with the logarithm. So first of all, let's compute in the two limits. When epsilon goes to 0, this guy goes to 0. Nothing really bad happens over here. Okay? So in the lower limit, it's just simply 0. Okay? When epsilon goes to infinity, this guy explodes, right? But what happens over here? 0. 0. Okay? Who goes faster to 0? Who goes faster to 0?
Probably the
What is log of 1 minus x when x is small? It is minus x. Right? It is minus x. The Taylor expansion of a logarithm around 1 of 1 minus x when x goes to 0 is minus x. Okay? So in the upper limit, what we have, this is an extremely small number. Okay, so we have epsilon to the 3/2 multiplied by whatever we have over here, which is minus e to the power minus beta epsilon minus mu. Okay? And it, in the epsilon goes to infinity, goes just to 0. Okay? Because this guy goes exponentially fast to 0, and this guy goes polynomially fast to infinity. Exponents always win polynomials, so we don't need this term at all. Okay, so what do we have eventually? So we have A over here, but A includes beta. We have beta from here. We have 1 minus, 2 minus, 3 minuses. Okay. So we keep up all those minuses. We can keep up, well, let's write it down with the ugly prefactor. So we have GV divided by 2 pi squared, 2m divided by h bar squared to the power of 3/2. Now here we have beta, here we had 1 over beta, so they cancel. We have a prefactor of minus 2/3, and we're left with an integral from 0 to infinity of, let's take this down. So we have e to the power 3/2 divided by e to the power of beta epsilon minus mu minus 1 d epsilon. Much nicer. Okay, great. So this is our side. Okay. Now, what I actually want to compute, it's not psi, it is the average number of particles. Why? Because eventually I will have this n to be very large. Okay, so nothing really happens when n is small. But when it's large, for fermions, we observed an interesting fact that mu Fermi is also very large, and so the interactions are not playing any role. So I want to compute n, and at some point to take this n to be very, very large, because I can control n experimentally. I can put a lot of particles inside a box. Okay, great. So what is n? Do you remember? Minus d psi to d mu. Okay. How do I remember this? The grand canonical potential is psi equals to E minus Ts minus mu n. Okay, so the Legendre transformation, since I took n out, the mu that appears over here, it is d psi to d mu, and be the minus sign. Okay, so if you remember what's the Legendre transformation from the energy to the grand canonical potential, you always know how to obtain all the different variables. Great. So we take this guy. Okay. Questions? No. And we take the d to d mu of whatever is inside. Right. Now, all the prefactor is just a prefactor. We don't care about it. Okay. So we have the d to d mu of this. So it's minus 2/3 gv 2 pi squared.
The minus cancels out.
Minus cancels out. Thank you. So we'll have the minus over here. 2m divided by h bar squared 3/2 d to d mu 0 to infinity e to the 3/2 divided to e to the power beta epsilon minus mu minus 1 d epsilon. Okay. What we do next? Okay, so if we are mathematicians, we try to prove that this integral is converging to something homogeneously, and when you're a physicist, you just say, it's here, right? You can do it. Why not? Right? So this is what we do. We switch the order of integration and differentiation, and we really don't think too much about whether the convergence is homogeneous or not. Who cares? Okay, so again, this is b. So this is b, an integral from 0 to infinity. And let's take the derivative with respect to mu. So what do we have over here? It is the following. So epsilon to the 3/2 stays as it is. It's 1 over e to the power beta epsilon minus mu minus 1 squared. Okay. Here we have minus 1. Okay. And we have e to the power beta epsilon minus mu multiplied by minus beta. And all of this d epsilon. Yeah. Okay. So minus minus cancels. And what we eventually have is this number b multiplied by beta, an integral from 0 to infinity of epsilon to the 3/2 multiplied by e to the power beta epsilon minus mu divided by e to the power beta epsilon minus mu minus 1 squared d epsilon. Okay. So this is the average number. Okay, so what we do with this integral, make it nicer. What do I mean by making it nicer? Let's solve it by parts. Integration by parts. I look on this guy separately, and I look on this guy separately. Okay. Now, but instead of taking another derivative of this guy and making an integration of this guy, which is simple, I will make an integration of this part. Okay. So what is an integral of e to the power beta epsilon minus mu divided by e to the power beta epsilon minus mu minus 1 squared d epsilon? Okay. So I will call to e to the power beta epsilon minus mu minus 1 squared. Can I call it? What can I call it? U is nice? Or u squared? U is nice. Okay. Back down.
Stas,
Um,
I think you lost a beta along the way.
Where?
A is G divided by beta.
Yes, multiplied by beta. Okay. That's fine. This is why I changed the beta over here. I wanted to include the 2/3.
Yeah.
Okay, so let's call it u without this square. Let's call it u. It's easier. Okay, so if this is u, all right, what is du? Du equals to what? Du equals to e to the power beta epsilon minus mu multiplied by what? Beta d epsilon. Okay? So this is our transformation, and this is why I called it, because, well, we have this part just without the beta over here. If you're tired already from all the integrals, it will continue for another half an hour. Okay, so what we have, that this integral, it is what? It is an integral of d, it's 1 over beta, of du divided by u squared, which is beta multiplied by minus 1 multiplied by u minus 1. 1 over beta, thank you. 1 over beta, which is minus 1 over beta, and we know what is u, 1 over e to the power beta epsilon minus mu minus 1. So all of this is transformed to what? Transformed to epsilon to the 3/2 multiplied by minus beta 1 over e to the power beta epsilon minus mu minus 1 in the limits 0 and infinity. Okay. And we have an integral with minus an integral from 0 to infinity. The derivative of epsilon to the 3/2 is what? Is 3/2 epsilon to the 1/2 multiplied by minus 1 over beta multiplied by 1 over e to the power beta epsilon minus mu minus 1 d epsilon. Now let's look on the first part. It's exactly the same game. When epsilon goes to 0, this guy goes to 0, this goes to some constant, so it's just 0. Okay. When epsilon goes to infinity, this part diverges. This guy goes to 0, again exponentially fast, because we have 1 over beta epsilon over here. When epsilon diverges, this part diverges exponentially, so we don't care about this part at all. Okay, so eventually what we obtain, that n equals to b beta multiplied by, so we have a minus multiplied by 3/2 1 over beta, and an integral from 0 to infinity of epsilon to the 1/2 divided by e to the power beta epsilon minus mu minus 1 d epsilon. Now we have 2/3, we have 3/2, so if we substitute everything inside, we obtain that the average n is beta cancels, 3/2, 2/3 cancels, we have gv divided by 2 pi squared 2m divided by h bar squared 3/2, and an integral from 0 to infinity epsilon to 1/2 divided by e to the power beta epsilon minus mu minus 1 d epsilon. Much nicer. Okay. But can we see something out of this integral? So what if n is large? So it's somehow restricted. Okay. All this integral, still we don't see, well, maybe there is a problem, maybe there is interesting physics, maybe something. But we don't really know what to expect from it. The moment that you have a general expression that you don't know how it behaves in specific limits, you just have to push forward. Okay? Maybe if we'll take this integral and solve it and represent it by something different, okay? Maybe, just maybe, we'll see the interesting physics that I promised you. Okay, so we take this integral and we want to continue forward just with this integral. So notice that the interesting part is this mu, which we don't really know what it is, but we do know that it can't be that mu is exactly 0, right? Because what we told each other yesterday, what I taught you yesterday, that mu have to be lower than any potential energy or any energy of your system. Okay, so if our lowest energy is 0, mu have to be lower than 0. Okay. Now, instead of carrying all this mu around, what we'll do is that we call this quantity e to the power beta mu. We call it zeta, and this is fugacity. In Hebrew, plitut. And we'll operate now on with this fugacity. Now notice that here it's not without the minus sign. It will play a specific role. So the average n, it is this gv divided by 2 pi squared 2m h bar squared to the power of 3/2, an integral from 0 to infinity of epsilon to the power 1/2. Here we have the fugacity to the power minus 1, e to the power of beta epsilon minus 1 d epsilon. Okay. I would like to make something different of this integral, and specifically at some point of time I would like to expand in Taylor series this part over here. Okay. So I'll take everything upside. So I have an integral, let's call it, so what we have a, b, c is not a good number, d, e we have, let's call it g, okay, let's call it g. This is the big G. So we have g multiplied by an integration from 0 to infinity. Here we have this fugacity to the power without any power minus 1, epsilon to the power 1/2. What else? We have e to the power beta epsilon minus, and here we have 1 minus the fugacity to the power 1, e to the power minus beta epsilon, the epsilon. Okay. Now notice now the specific representation. So what we have in the denominator, we have 1 minus the fugacity is e to the power beta mu. Mu is probably smaller than 0. Beta is 1 over k Boltzmann T, so it's a positive number. So this guy is what? It is something that's larger than 1, okay? But it can be very small, okay? Or very close to 1. Here we have e to the power minus beta epsilon, and this epsilon is larger than 1, so probably, okay, all this number over here is smaller than 1, okay, for any given epsilon. Okay, so if this number is smaller than 1, in the following we can expand all of this. We can expand all of this in a Taylor series. Okay, that's would be the goal. Because I don't know how to solve this integral exactly, but sometimes the integrals where I have some denominators, I can expand part of the functions, right? I can expand part of the functions and then solve the integration part by part of the sum that I will obtain. Okay. Now another thing that bothers me is that I have epsilon to the 1/2, and here I have e to the minus beta epsilon. You know, it's not such a good deal because the squares, they always complicate things around. So I would like to introduce a transformation of coordinates. So specifically, I would say let's call epsilon as x squared. Okay. Now why x squared? Because I do know how to solve Gaussian integrals. This is something that I do know. And you also know how to solve Gaussian integrals. Okay, and I have here 0 to infinity. So if I have some sort of a Gaussian integral, probably I will be capable of solving it. Okay, so if I have epsilon equals to x squared, I know that d epsilon equals to 2x. All right, so with this transformation over here, what do I have? I have that it equals to this big G. We can take the fugacity out, an integration from 0 to infinity, right? Here we have x, here we have e to the power minus beta x squared, and in the denominator we have 1 minus the fugacity e to the power minus beta x squared dx. 2x. Wonderful. Now take this 2 out, and then here I have x squared. Okay, so write it down as g, the fugacity, and integration from 0 to infinity. 2 out. Here I have x squared, e to the power minus beta x squared, 1 minus the fugacity, e to the power minus beta x squared dx. What will be the next move? The next move is to use Feynman. Okay. I told you that I like Gaussian integrals. You should also like Gaussian integrals. So I noticed that this guy, I can make something out of it, okay, which is x squared e to the minus beta x squared equals to minus d to d beta e to the power minus beta x squared. Right? So I plug it inside, but I do it carefully. I obtain that is 2g, the fugacity, an integral from 0 to infinity, minus d to d beta of what? Of e to the power minus beta x squared divided by 1 minus the fugacity, and here I have e to the power minus beta x squared dx. Okay, next step is realize that maybe this Feynman can be extended. So the next step would be, let's expand it. I know that 1 over minus x, it's a summation, n goes from 0 to infinity of what? 1 over n factorial x to the power n.
No.
No?
This is just x to the power. Okay.
Yeah.
Yeah, okay.
That's
What is the one
exponential.
when we count for e?
Yes. Okay. Sorry. So x to the power n. Okay. So this is 2g, an integral from 0 to infinity, minus d to d beta, e to the power minus beta x squared. Here I have a summation, n goes from 0 to infinity, of xi e minus beta x squared to the power n dx. Fine? Looks fine. Okay. Now, let's take everything out. What I mean by taking everything out, I'm taking everything that is not related to the integration of x outside of the integral. Again, I am assuming that eventually everything will converge, so I don't care what I do first. Summation, integration, okay? Good physics approach. So we have minus 2g xi. What else? I have what else I have? A sum, n goes from 0 to infinity, of xi to the power n, fugacity to the power n, an integration from 0 to infinity of what? Of e to the power minus beta x squared n multiplied by d to d beta, right, of e to the power minus beta x squared dx. Yes? Okay. Now it is minus 2g. I'm looking on this guy and saying, let's do, it's just a derivative of what? What is this? It's derivative. So if I had a derivative of e to the power minus beta x squared to the power n plus 1. Okay, over 1 n plus 1. And I will take a derivative out of this with respect to beta, d to d beta. Okay? What will happen? So n plus 1 goes down, so I have n plus 1 divided by n plus 1. Okay? Now multiplied by e to the power minus beta x squared to the power n, multiplied by d to d beta of e to the power minus beta x squared. Right? So all of this, let's take 1 over n plus 1 out. So all of this, okay, this is just 1 over n plus 1, 1 over n plus 1, d to d beta of e to the power minus beta x squared n plus 1. So I have minus, minus 2g minus 2g fugacity. Let's put the fugacity inside the sum. A summation n goes from 0 to infinity. Fugacity to the power of n plus 1. And I have an integral from 0 to infinity of d to d beta of 1 over n plus 1 multiplied by e to the power minus beta x squared n plus 1 dx. Let's take this outside of the integration. So we have minus 2g, a summation of n goes from 0 to infinity of fugacity to the power of n plus 1 divided by n plus 1. Okay. And here I have d to d beta, an integral from 0 to infinity of e to the power minus beta n plus 1 x squared dx. told you that I like Gaussian integrals because we know how exactly to solve them. So what is this integral equals to? It is 1/2 square root of pi divided whatever is standing over here. Beta n plus 1. Right? Okay, so what we have is minus 2g summation n goes from 0 to infinity. Fugacity to the power n plus 1 divided by n plus 1. And let's take d to the beta of this guy. So it is 1/2 square root pi divided by n plus 1. And here I have beta to the power minus half. So we have minus 1/2 beta to the minus 3/2. All right. Okay, now what was g? I already forgot what was g. Do you remember what was g? Large g.
GV 2 pi
divided
squared.
gv 2 pi squared
2m divided h bar by 1.
h bar m
The power of 3.
halves. I had a number over here?
No.
No, I haven't. All right. I haven't.
About what?
Sorry?
About what?
H bar
Squared.
squared. Okay. Now let's see what happens over here. I have 2, and I have 2, and I have 2. So in total, I have 2 over here. I have beta. I can put it inside. All right. And I have a summation. I have a summation of what? Of n goes from 0 to infinity of a fugacity to the power n plus 1 divided by n plus 1 to the power 3/2. Okay. And we use something which is known as a polylogarithm function. F alpha of z equals to a summation of what? From n goes from 0, from 1 to infinity of z to the power alpha divided by alpha no, alpha it's over here, so n to the power alpha, z to the n and to the power alpha. Here, so we had 1/2 from the integration, from the Gaussian integration. This is 1/2, because the integral from minus infinity to infinity is square root of pi. And here it is 1/2 over square root of pi. Okay, this is just why we have 1/2. So this is 1/2 over here. And the other 1/2, right, from the derivative of beta to the power minus 1/2. Okay, so the final result.
Where does the square root pi go?
Where does square root pi go? Where is square root of what? Oh. So we have another square root. So we need square root of pi. Square root of pi, 2. Okay, now let's write it down. With everything inside. Average n equals to GV divided by lambda t to the power of 3 halves, okay, multiplied by f of 3 halves of fugacity. And this is a polylogarithmic function that you can export. Polylogarithm. Okay. What is lambda t? Lambda t is whatever we had out of here, right? So what we had, 2m h bar beta, so we have 2 to the 3 h bar beta pi, so we have lambda t, it is 2 m divided by h squared beta. Wait a minute about this too. We have pi over here, and let's take care of this too. So we have 2 to the 3 halves. Okay, we have 2 to the 3. Okay, so 2 to the 3 halves is just 2 over here. This is lambda t. Great. Now, this is also called thermal wavelength. Okay. That is just a constant for us. Look, it depends on the temperature. Why? Because the temperature, beta is the temperature, so we can write it down as K Boltzmann T m divided by 2 pi h bar squared. Okay. This is the generacy, the volume, and something that depends only on the fugacity. Okay. So again, neat formula, a lot of work. It took us an hour to get here. Okay. A little bit less. So now let's explore how this polylogarithmic function looks like. It's actually a little bit boring. Okay. You can explore it, you can expand it, but it's really, really, really boring. So this is your fugacity. Okay, this is f 3 halves of fugacity. Now remember that the fugacity, it's bound. What is the fugacity? It is e to the power beta mu. Mu is bound, so the fugacity is bound. Mu cannot overcome 0, or very, very, very small number, our ground state. Call it 1. Okay. And now you plot this function. And it starts linearly, then it grows, it grows, it grows, it grows. Its derivative explodes, but it reaches a finite point. Okay? So at 1, the value of this function is 2.612. And this 2.612 have enormous implications. Enormous implications. Because look what we found. We found that n, the average number of particles, multiplied by lambda t to the power of 3 halves, divided by GV, well, we know that is f 3 halves of the fugacity, right? But the right hand side smaller or equals to 2.612. Okay. So we have found a bound to this left-hand side. The average number of particles, the degeneracy, the volume of the system, and the thermal wavelength. Thermal wavelength, well, I can make it small or large as possible because I can control the temperature. Okay. The same holds for the temperature over here, for the number of particles. So, number of particles or the volume is something that I can control, right? I can make my volume larger, I can make my volume smaller. So eventually it's going to be something that I control experimentally. And also n is something that I can control experimentally. Okay? I can put more particles and I can put less particles inside the system. So everything on the left hand side is something that I can control. But what all those long derivation tells me, no, you can't. Right? Because this ratio have to be always smaller to 2.612. But if I put a lot of particles in my system, surely I can overcome this 2.612. Okay, so this is a conundrum. All my derivatives, all my derivations showed me that I have a ratio that is smaller than a given number. The physics and the experimental facts tell me that this guy is unbound. Absolutely unbound. Right? So I can take V small and large, okay? And I can make this ratio as large as I want. Remember, it won't work when n is small, it's like in the fermions. Okay? The physics appeared when n was large. The same goes over here. When n is small, yeah, there is a bound. I don't care about this bound. The ratio n to the v is something. But when n is large, there is nothing, absolutely nothing, that stops me from putting a lot of particles inside the system and making this ratio extremely large. Okay, so this is a paradox. Okay? Some sort of a paradox. We expect this ratio to be unbound. All our calculations, all our math, the 1 hour that we invested in following this integration by parts, expansion, Fermi tricks, twice, etc., leads us to this trick. Which, what is right and what is wrong? Is our physical perspective of that this ratio n divided by v is unbound is correct, or our mathematical results that it is bound by 2.612 is correct? What do you think? And how we resolve it? Something went wrong, right? Absolutely something went wrong. Yes?
Stas, isn't the notion that, isn't the our assumption of the derivation of everything about the boson gas statistics, don't we assume that that n is unbound, like where
You just strengthened my claim. N is unbound, right? You just say.
No, I mean it's not something that we can control. It's where.
Of course we can.
But
Of
we're
course we
adjacent to an
can.
infinite
No,
graph.
you've forgotten what I've told you. Of course we can. This is the only thing we can control. We cannot control mu. And mu is somehow going to be defined by the number of particles that we put inside the system.
But if
We cannot control mu, we can control n. And we can push more and more particles inside the system. What you're telling me is by some magic, those particles are going to disappear.
no, I'm saying that if we assume
Don't stick to the
that
math.
states
No,
are unbound,
you are wrong.
then
You are wrong. Why you're wrong? Because there is a specific connection between what is a parameter and what is an outcome. I can fix mu and find n. Or I can fix n and find mu. Right? That's it. It doesn't matter what I fix. I developed everything by fixing mu. But eventually, I can now redo all my steps backwards and say n was a specific number, therefore mu has to be such and such. Okay, that's it.
G גם יכול לקרוא, לא?
G, 1, 2, 3, 4, 5, 6. It's a number, not very large. Okay? I can pick a specific number of particles that have spins 1 and plus 1. So G is 1, 2, 3. It's an order of 1. Temperature you can control. You can make it large, small, big, whatever. Yes.
So the only assumption we made here is mu being a negative, right? Do we make any more assumptions?
No. Well, we made some specific assumption, right? We made an assumption. I told you, you believe me, that the spectrum is continuous, right? I told you, look, we have a continuum spectrum and we have this density of state. So density of state is correct. But is the spectrum is truly continuum? The only assumption that we somehow put inside all of this, which is maybe questionable, is that, well, Stas, those are quantum particles, right? And those quantum particles, they have they have discrete spectrum. The spectrum is very, 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 very dense. And the only assumption that I made from start is that I can look on this very dense spectrum and say to you, it's a continuum. There was an approximation made, right? I had a summation over all possible epsilons, okay? And I said that everything is the epsilon. That's the only point where we had any specific assumptions all the way. It started at the beginning at all, but this is the only point where we might get wrong something. Okay? Now let's try and resolve it, see what actually happens over here. Okay, so what are epsilons? What are our energetic states? So they're actually quantum numbers, right? Because where the epsilons are coming from. And they're not just number. I'm saying, oh, it's a kinetic energy, and the kinetic energy can be whatever you want. It's a solution to a Schrodinger equation, right? So you have taken quantum 1, quantum 2, you solve particle in a box. When you solve particle in a box, in one dimension you get one quantum number, in 3 dimensions you get 3 quantum numbers. You have nx, ny, and nz. Okay. This is your energy, which is p squared divided by 2m, and you solve it, you obtain that this is h, Planck constant, not h bar, it's h squared divided by 2m, 1 over lambda x squared plus 1 over lambda y squared plus 1 over lambda z squared. Okay? Now, what are lambda x and lambda y and lambda z? They are somehow the waves that survive the solution of the Schrodinger equation. So you know that nx multiplied by lambda x divided by 2, it is the dimension in the x direction. And you know that ny multiplied by lambda y divided by 2, it equals also to L. And you know that nz multiplied by lambda y divided by 2, it's also equals to L. Okay. This is something that you know. Right, so I know that lambda x equals to 2L divided by nx, which equals to 2v to 1/3 divided by nx. And I know that lambda y equals to 2v to 1/3, v is the volume, divided by ny. And I know that lambda z equals to 2v multiplied to 1/3 divided by nz. Okay? So I can plug it inside invite it inside and see what is my energy. I plug it over here. So it equals to h bar divided by 2m, and I have 1 over lambda x squared. It is what it is. It is v to 2/3. No, it is nx squared. Nx squared divided by 2 v to 2/3 plus 2 or 4? 4. Yep. Plus ny squared divided by 4 v to 2/3 plus nz squared divided by 4 v to 2/3. So in total, we obtain it is h squared divided by 8 m v 2/3 nx squared plus ny squared plus nz squared. Okay. Okay. Now, if I'll do this and I plug specific numbers inside. Okay, so let's look. We say the density, it is indeed a dense system. Okay, so let's think, or let's calculate what is the distance between the ground state where nx equals 1, ny equals 1, and nz equals 1, right? And the next state. So I want to calculate what is epsilon 2, 1, 1 minus epsilon 1, 1. Because epsilon 1, 1, 1 is my ground state. Okay, so what do I obtain? I obtain that it is 6h squared divided by 2 mv 2/3. Okay, I plug specific numbers. I'm looking on helium, all right, 4. So the mass is approximately 6.6 multiplied by 10 to the minus 27 kilograms. And I take a liter of this thing, so V is 10 to the minus 3 meters to the third. And I obtain that epsilon 211 minus epsilon 111 is approximately 2.5 multiplied by 10 to the power minus 37 joules. Okay, so it's indeed very, 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 very dense. If I want to calculate it, so if I'm taking epsilon 211 and make this difference, I divide it by K Boltzmann, I obtain that it's approximately 10 to the minus 14 Kelvin. If I'm measuring it as a function of some temperature. It's extremely dense, unbelievably dense, right? So the assumption that I can go from a summation to an integration is very, very satisfying, right? It's extremely small numbers. Extremely small numbers. So yeah, the transition from the summation to the integration is good. Is it enough? But we still have this problem over here, right? The guy won't go above 2.612. Where else we can have a problem? Again, the only assumption was this. Density of state, but density of state is fine. It's very much fine. It's much finer than in the Debye model because the solutions of the Schrödinger equation are indeed waves. They're free waves with specific boundary conditions. Okay. Yes?
Perhaps above a certain threshold, we can no longer integrate. We do transition to
Well, you always can integrate. Right? You always
no,
can integrate.
like something akin to the Debye frequency or.
There's no physical problem with having very large energies.
Wait,
Yes.
did we account for degeneracy?
Yes, yes. Yeah. Anything else? Can we always integrate? Can we always integrate? So integration, bring you back to whoever studied Calculus 101 in the math department, Calculus 201. Seen those problems. I don't know if it was taught in the physics department. So the approximation of a function or an integration of a function by integral goes like this. So let's assume that you have a discrete spectrum, right? Because what eventually we have done? We integrated over a specific spectrum of a given function, right? We had a summation of epsilons of a log of something, right? This is what we've done. We included the the density of state, but this is what we've done. It was discrete. Okay. What I mean by discrete, so this is our function of epsilon as a function of epsilon. And what we've done is, well, it has a value over here, and 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 a value over here. Well, it has a specific shape. Now, all those points are extremely dense one to each other. Okay. So what we've done, what we had to do is to look on all the values over here, and for each value of epsilon, you modify those quantum numbers. You go and you pick a specific epsilon, you pick a specific value, the given value of your function, and you sum them up. Okay? Now, it's very hard to sum things up, so we usually do an integration. So we say, all right, we approximate this function because it's very dense. Okay, we approximate this function because it's extremely dense by a continuous function. And what we do is we calculate the integral. This is what we have done. Okay. And the assumption, okay, there are several assumptions, but one assumption is that those guys have to be extremely narrow to each other in order for this to work. Okay. Great. This is all very good, and works well, but the mathematicians have additional conditions for the approximation of a sum to the integral for it to work. And what is the additional condition? The additional condition is, well, it will work unless at some point you have something that goes to infinity. Unless if at some point your function is not just diverging, it's in a specific region. If it's diverging in a specific region, it's fine. But if there is a singular point where only for this point, this function explodes. Okay? So it's like a delta function contribution, right? In some sense, if I have a delta function contribution, I cannot just say, well, I just integrate over everything and that's it. I have to treat this one specific point very carefully. Okay? That's it. Right? So what happens in our case? We lower the temperature. Okay? We know that we have discrete states in our system. Okay? We know that we have discrete states in our system. So we look on those states and we count for each state this logarithm of 1 over z, whatever. Okay? What happens to the occupation of each given state? Okay? So what is that we know? Where is this? It is over here. Okay. What is this we know? We know the following. At the ground state, the average number of particles. Okay? What is the average number of particles at the ground state? It is, we know this. It is 1 over e to the power beta epsilon 1 minus mu minus 1. at the ground state, if you want to calculate, before going to all those continuum approximations, summation, etc., look at the ground state. Pick your quantum numbers 1, 1, 1, all right? Calculate the specific energy, and this is the average number of particles at your state. Okay. Now, what happens? As you lower the temperature, okay, mu goes up. We have seen this. Okay? As you lower the temperature, mu goes up, and eventually, so T goes to 0. Mu, it have to be always smaller than epsilon 1, 1, 1, right? But it approaches epsilon 1, 1, 1. Okay? But when it approaches epsilon 1, 1, 1, this guy is small. So we can expand this, right? So we can expand this in the following. It is 1 over 1 plus beta epsilon 1, 1, 1 minus mu minus 1. Right? So 1 and minus 1 cancels. So we know that n0 is approximately K Boltzmann 1 over beta epsilon 1, 1, 1 minus mu. So we can put beta over here, so it's K Boltzmann. Now, in the limit where mu approaches epsilon 1, 1, 1, this is a very large number. Okay? So this goes to infinity, or basically diverges, when mu approaches epsilon 1, 1, 1. Okay? Okay. This is the lowest possible state. What happens at the state above? So what I'm saying, the problem might be is that I have an extremely large number somewhere, okay, and the next guy is going to be much, much, much smaller. Okay. So let's compute the average number of particles at the next level, not at the ground state, but at the next level. So what happens at n2, 1, 1? We know that is 1 over e to the power beta epsilon 2, 1, 1 minus mu minus 1. Okay. So I also, this is still a small number, so that's 1 over 1 plus beta epsilon 2, 1, 1 minus mu minus 1. So 1 minus 1 cancels. But I want to write it down as 1 over beta epsilon 2, 1, 1 minus epsilon 1, 1, 1 plus epsilon 1, 1, 1 minus mu. Okay. And it is K Boltzmann T. Epsilon 2, 1, 1 minus epsilon 1, 1 plus epsilon 1, 1, 1 minus mu. Because Stas is also a small number. Why? Because, well, you just showed to us that the differences between epsilon 2, 1, 1, 1 and epsilon 1, 1, 1, it's a very small number. But epsilon 2, 1, 1 minus epsilon 1, 1, 1, it's always greater than 0. Or let's call it, it is greater than some c greater than 0. It never goes to 0. Never goes to 0. But mu can approach epsilon 1, 1, 1 as much as we want. Okay? So n0 is not limited from above. Okay? n2, 1, 1 is limited by what? By K Boltzmann T divided by epsilon 2, 1, 1 minus epsilon 1, 1. Right? So there is a limit of how many particles are sitting at the next excited state, and there is no limit to n0. So what happens in reality? what is the ratio when I plug everything inside? When I plug everything inside, and I have a litter of particles, and many particles inside the system. When I plug everything inside, I will obtain that N211 divided by N0, it's on the order of 10 to the minus 7. Okay, so think about it. I have a function. As a function of epsilon, and everything is neat. Okay. And everything is neat, but at 0 or here, I have a delta function. That's what mathematically I have. Okay. And I haven't treated this delta function at all. So the density of state are absolutely fine. The states are very, 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 very much dense. But there is a specific state where there's huge number of particles, and the number of particles that can sit at this state is actually unbound, and the next excited state is bound. Okay? It is bound. There is a specific bound given by this guy. It can be large. Who cares? Right? Still, who cares? So what actually happened is that if I'm looking on the energetic level for low enough temperatures, I will get huge number of particles that instead of, for fermions, everybody piles up here, everybody piles sideways. You can say, Stas, so what? So you have a little bit of more of particles on the lowest level. It's not a little bit. It's a macroscopic fraction. Think about it. Those are microscopic states. So the assumption is there is a microscopic number of particles for each state, and together they give me the macroscopic number of 10 to the power 23, the Avogadro number. But what I'm telling to you is that there is one specific state, the lowest state, that for low enough temperatures, when we approach somewhere over here in this region, when we approach to this region, the macroscopic number of particles are sitting over here, piling up at the same energetic state. Instead of going up, they're going sideways. They're all sitting together exactly at the same energetic state. Okay? So where it approximately happens. Where it happens approximately. So it has to happen when we approach this guy. Right? It has to happen when we approach this guy. So what we know, that there should be some critical temperature okay, where this part equals exactly to this part. Okay. So we know that n lambda t c to the power of 3/2 divided by g v equals to 2.612. Okay. So getting out, what is lambda tc? Do you remember? I don't remember. What is lambda t? We had an expression. No, there is no n inside. There is no n inside. There is no n inside.
M.
M. Okay, so lambda t was m k Boltzmann bar squared. Okay. So what we obtain is that lambda Tc leads to a specific critical Tc, okay? And this, we get out of this that, what? So lambda Tc equals to 2.612 multiplied by g v divided by n, okay, to the power of 2/3. So we obtain that the critical temperature, it is 2 pi h squared divided by m k Boltzmann multiplied by this 2.612 multiplied by G divided by the average number of particles, V 2/3. So take a macroscopical system with large n or large value or V to the third, lower your temperature enough, okay, such that when n is extremely high, okay, and you will get this critical temperature. So for helium, this temperature was found around 3 kelvins. For helium 4, this guy is around 3 Kelvin. Okay. You go and measure in reality, and you find that in reality it is an experiment. It is 2.17 Kelvin. Extremely close. Remember, we forgot any interactions whatsoever. So interactions matter a little bit, not too much. But the idea is, what happens in systems is that you can transit from specific distribution of particles among different states to a situation where the majority of your particles, huge number of your particles, are sitting at the lowest stage possible. This is called Bose-Einstein Bose-Einstein oh, I forgot the state. Condensation, yeah, condensation. Condensation. Sorry. Okay. So what happens in Bose-Einstein condensation? If you have enough particles in your system and you lower your temperature, at some point you'll hit this limit, 2.612. Okay? And above this limit, something else has to happen. Now, but it can't because your integral or whatever they give you. What happens is that there is a macroscopic number of particles sitting at your lowest state and you haven't counted them properly. Okay, so for high enough temperatures, there is no delta function. Nothing happens. Your integrals are fine. Everything is fine. You lower the temperature enough, there is accumulation of particles at the lowest state. You can no longer integrate this. You have to treat it separately, okay? And this gives you another contribution, okay? So all our results are good, but we forgot something. We forgot this lowest state, that below this critical temperature have to be accounted for. Okay? So this is what we are going to do in the, next. But this is a very surprising result, okay? And it's in a very big contrast to the Fermi behavior. Fermi behavior, they pile up upwards, okay? And you have macroscopic number of particles, so therefore your mu Fermi is extremely large. Here they have pile not downwards, they pile sideways, so therefore everybody are sitting in exactly in the same state. And from quantum perspective, and this is the neat result, we won't discuss it, the neat result is if all the particles are sitting exactly at the same state, they have exactly the same wave function. And if you want to excite one of them, you can't, because you don't know who is who, right? So you obtain some cool results like superconductivity, okay, or superfluidity. For helium, this helium flows without any friction. Because what is friction? Friction is excitation that bring your particle to an upper level, right? And from this upper level, you have to lose energy to come backwards. But if you cannot excite anybody, because they all have exactly the same wave function, you don't have friction. Okay. All right, a little bit more about what happens below the critical temperature and how we find it next week. Thank you all. Vole po, תשאל אותי. כן.
לא.
זהו, זה. זה המיו, אתה המיו. המיו זה מה שחשוב.
אין איזה משהו פיזיקלי שאתה...
לא כל כך, המיו זה הפוטנציאל הכימי שלך.